Hello, I welcome you all. The problem reads the shaft is supported by a smooth thrust bearing at A and a smooth journal bearing at B. Draw the shear and moment diagrams for the shaft. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. So let's draw the free body diagram. We have AY there, we have AX there, and then we're going to have a BY there. And then we'll have an equivalent force. This is a triangular distributed force, and this one is going to be equal to half times the height. Maximum height here is 300 times the base, which is 6 feet. Therefore, this is going to be equal to half by 6 is 3 by 300. This is 900 pounds. And this load is positioned, or its location is 2/3 of 6, which is equal to 4 feet, right? 4 feet. Great. So quickly let's apply the equations of equilibrium. Summation of moments about point A equal to 0. There we go. So we have a 900 times 4. This is clockwise, so it's negative, plus by 12, right, equal to 0. Therefore, our by is going to be equal to, grab your calculator, 900 by 4 divided by 12. This gives us 300. All right. So this is 300 pounds, right? Sorry. So this is 300. So 900 by 4 divided by 12. 300, and then summation of forces in the y equal to 0. What do we have? We have AY plus BY minus 900 equal to 0. Therefore, our AY is just going to be equal to, we know what BY is here. Okay. So AY, so we have BY, which is 300 minus 900. This gives us 600. Therefore, this is equal to 600 pounds. And then summation of moments in the x direction equal to 0. We have AX equal to 0. All right. So we have AY equal to 600. We have BY equal to 300. AX equal to 0. All right. Let me get rid of this so that I have some space. Great. So this one is 300 pounds. All right. So what we are going to do now is we have intervals. Let me also indicate this as interval C. So we have interval AC and CB. So in the first case, I'm going to section this beam here, and then I'll be moving from A going in this direction. So let me draw this beam quickly. So I have a load there which is 600 pounds. 600 pounds. This point is A, and then I have this triangular load. This triangular load, okay, whose function, I'll need to find the function. So let's find the function of this load. So this is A and this is C. This point is 300 pounds. 300 pounds per feet. Okay, it's like this. All right, so we are using q over x. We are moving in this direction. Okay, it's going to be equal to m, which is the gradient, x plus y, plus c, which is the intercept. We know that in this particular case, c is equal to 0. Remember this equation, right? How to find the equation of a linear equation, right? Equation of a straight line, right? So c is equal to 0, and our gradient m is going to be equal to change in y divided by change in x. Remember this? So our change in y here is going to be equal to so if this point is a here has coordinates 0, 0, okay, 0 in the x and 0 in the y, and then this point here, okay, it has coordinates 6, because this distance from here to there, this is 6 feet, this is 6 feet. So these coordinates here, they have 6, 300. All right, therefore difference in y will be 300 minus 0 divided by 300 minus 0, and then in the x we'll have 6 minus 0, right? And then finally this becomes equal to 300 divided by 6. This is a 15. Okay, hence our q of x is just going to be equal to 50x. All right, so this is what this is the equation that defines this loading. Okay, so that q at 6 meters is supposed to give us 300 pounds, right? 300 pounds, okay, per feet, right? All right, so this is what determines this is our equation. So this equation is 50x. This is what we are going to indicate here, 50x. Let me write it in just black, 50x. All right, and therefore our equivalent force for this one is just going to be equal to, since we are moving from there to there like this, and this is our x, this is our x, this is going to be equal to half times 50x times x, and it is giving us 25x squared. All right, and the position for this is okay, 50x times x is equal to 25x squared, and then the position for this this position here, let me write this somewhere. I write it here. This is the maximum load, 50x, and then we are looking at this position here from there to there. This position here is going to be equal to one third of x. All right, then here we expect, if this point here we're going to call it 1, then the other point 2 here, so this point here is 1, the point where we're doing the sectioning, right? And we have this one is going to be equal to v1, and then we'll have the moment m1. So we've drawn the free body diagram. We have drawn the free body diagram in the section at 1. So now let's apply the equations of equilibrium. So summation of moments about 1 equal to 0, and clockwise being our reference. What do we have? We have 25x squared times 1 over 3x, okay, and then we have minus 600 times x, and then we have plus m1 equal to 0. Therefore, our m1 is just going to be equal to m1 is equal to minus, let's multiply this. So we have 25 divided by 3 minus 8.33 x cubed, right, plus 600x. Okay, great. So, and then summation of forces in the y direction equal to 0. What do we have? We have 600 minus 25x squared minus v1 equal to 0. Therefore, our v1 is equal to minus 25x squared plus 600. Great. This is about it. Let's also consider the other part, the section at this point. Okay, and then we are going to use the right hand section. Alright, so we'll be moving from this side. So we're using the right hand side section here. We're using the left hand side section. So let's draw this quickly. So it is like so. We have a load there of 300. This point is B. Okay, we have this point is 2. We are going to have V2. We're going to have V2 like so. V2, and then with moment M2. And this is X, and we are moving from here to there like that. So let's apply the equations of equilibrium. Summation of moments about point 2 equal to 0. What do we have? We have 300 by x plus minus 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 m2 equal to 0. Therefore, our m2 is just going to be equal to 300x. And then summation of forces in the y equal to 0. Okay. What do we have? We have 300 plus v2 equal to 0. Therefore, our v2 is going to be equal to minus 300. Alright, so we are done with the equations. What we need to do now is to start plotting. So let's just prepare our lines. So let's prepare the first one, which is this one. Maybe it comes a little bit down, maybe here, right? And then we have another one maybe somewhere there, and then another one maybe somewhere there. Great. I think this is fine. There we go. So we have this point. We call this point A. Then we have C. Then we have B. And then we have a loading. A triangular uniformly distributed load like so. And then at this point here, At C, this is a 300 pounds per feet. Okay. This is B. Then we have a reaction at this point here at A, which is equal to 600 pounds. And then we have another reaction at B, which is equal to 300 pounds. Right. Okay. And this is the shear force diagram, and this is the bending moment diagram. Positive, negative, positive, negative. This point here is 0 and this is 0. Okay. And then we have this point here that just demarcates these two intervals so that we see what happens. Alright, something like that. So we need to find the values now in each interval, AC as well as AB. AC, we have AC and AB. Okay, so now let's find what V1 is when X is equal to 0. We are moving from A to C. So V1 at X, V1 when X is equal to 0. What's V1? This is our V1 here. Okay, it's a polynomial of degree 2. So we'll have a constant value when X is equal to 0, which is 600 positive. And then let me bring it a little bit down again like so. And then when V1, what is V1 when X is equal to 6 feet? Alright, let's plug it in there. That is V1. So it's minus 25 times 6 squared. Okay, plus 600. So we have a minus 300 pounds. Alright, and then we go to V2. V2 at B, because we are moving from B to C. At B when X is equal to 0, so we are using V2. And when you look at V2, it's just a constant, so it remains a constant value. Alright, so this one is a constant, is minus 300. V2 from B to C when X is equal to 6 feet, it still remains as minus 300 pounds, just a constant value. So let's do the plotting. I'm going to use green. So we start from A, moving towards C. At X equal to 0, we have 600. Let's imagine 600 is coming up to, okay, we take it up to there. All right. And let's look at this polynomial. Let's look at this polynomial. Is to the power 3. Okay. And then V1 when X is equal to 6, it is 300. Okay, this is just on the left hand of C. So we have these 2 points. 600, how do we join this? Again, we look at the function. Is the function opening like so? Okay, or is it opening like this? Okay, so we expect the function to open. If you are to plot this, it's going to open like that. Okay, it's going to open like that. So we are going to connect this like this. All right. There we go. So this point here is 600. Let me just write it. 600 pounds. And then this one here is 300. This one is 300 pounds. All right. And then from B to C, we've been told it is 300. Okay, it's 300. So we have 300 from this end, and 300 minus 300 rather. So we have this behavior here. We're going to have this behavior like this. Okay, just 1 minute. So okay, so we are going to have is a 300 throughout, which is a minus value. Okay, so we have a constant value there, and this is 300 pounds. This is minus. Okay, and then we have a positive value like so. All right. Okay, so we are going to also need to find this this length where we have shear equal to 0. Okay, this is where this function cuts the x-axis. So we are going to use v1 function, which is equal to minus 25x squared plus 600, right? So at this point here, this point, we expect shear to be equal to 0. So v1 will be equal to 0 at that point. And if it is equal to 0, let's find the value of x. So our x will be equal to plus or minus root of 600 divided by 25. So that gives us plus or minus, let's find what this value is. 600 divided by 25 root of that gives us a 4.9. So this value is 4.9. Of course, we'll get the positive value, right? 4.9 feet. We use this value to integrate the area so that we find the maximum moment, which will be at that point, right? So having found that, let's now move to the moments. We need to do the same like we've done for shear. So m1 at x is equal to 0. We are moving from a to c, and we are using this function here, okay, for m1. So when x is equal to 0, moment is going to be equal to 0, and that is what we expect because we have this support that resists only the translation forces. And then m1, when x is equal to 6 feet, that is from A to C, what will be our moment? All right, so let's find the moment. We can plug in 6, so we have minus 8.33 times 6 cubed plus 600 times 6. So we have a 1800.72 pounds feet. Let me do it again. Minus 8.33 times 6 cubed plus 600 times 6. Okay, 1800.72 pounds feet. So this is the moment when x is equal to 6 feet, right? Let's go to the other side, m2. So in this case, we are moving from B to C. So when x is equal to 0 at B, what is our moment? And we are using this value of m2. You've seen it's just a linear function. So moment at B is going to be 0 because of the support. We don't expect any moment there. And then what is moment when x is equal to 6 feet? 6 feet again from B towards C. All right. So let's plug in our value. So it will be 300 times 6, and this gives us 1000 800. Right. So let's start doing the plot. Okay. We have 0 at A, and then we have plus 1800 at x equal to 6 feet from A to C. And when we look at this particular function, is cubed. That's a polynomial of degree 3. Of course, we expect this function to open like so. All right, to open like so, and then it will begin to fall down somewhere. Okay, to open, it is going to open, and then there will be a point where it's maximum, and then it begins to fall, something like this. Right. So this point here, we already calculated this 1800.72, and then let's go the other side. From now B to C. At B, we've been told a moment is equal to 0 moment is equal to 0. Let me start from where I was starting from. Moment is equal to 0 when x is equal to 0 when x is equal to 0 at B, and then moment is equal to 1800 when x is equal to 6 feet from B towards C. So this is a straight line. All right, so it will just go and meet that point there. Of course, there are minor differences. We've seen 0.72 and we don't have any point there. It's because of rounding off. Okay, because of rounding off, that's the reason why we have these just minor differences. So this point here, we just give it which one do we give it? The highest value, lowest value? I'll give it the lowest value. Okay, it doesn't matter, even B to give it the other one, still fine. So let me give it 1800 pounds feet, this point. But we have another point here, which is the maximum point here. Okay, this is the point that we need to also to find. So we are going to integrate. We are going to integrate shear V1, okay, from 0 to 4.9 feet, so that we find this maximum moment. So we'll say maximum moment. Let's say maximum moment, max moment will be equal to integral from 0 to 4.9 of V1. What is V1? V1 is minus 25 x squared plus 600 dx. Okay, so if we integrate this, it becomes minus 25 x to the power 3 divided by 3 plus 600 x 0 to 4.9. Okay, so we'll need now to apply these values, okay, the integration constants. So what do we get? Maximum moment at that point. Grab your calculator. Okay, so I have minus 25 times 4.9 cubed, okay, divided by 3 plus 600 times 4.9. Okay, so I have 1959.59. So this point is 1. Let me write it. This point here is 1959.59. Okay, 0.59 pounds feet. So that's the maximum point. Shear here is the moment here is maximum. Is positive. So let me just give it just a minor shading like so. All right. So we say this value is 1959.59. Let me just check it again. 25 by 4.9 cubed divided by 3 and plus 600 by 4.9. Right, 1959.59. Right. I think that is about it. For this particular problem. We are done, and I hope the video was helpful. If it was, give me a thumbs up, like my video, continue subscribing to my channel. Bye bye, and see you in my next screencast.